The little thing for ice, yes. It's in there, it says I. All the viewers class. Okay, where was I? Before I was so rudely interrupted.
You were talking about the power and information.
What's going on at the molecular level that makes the reaction at the start
There's
faster?
more, we said that there's more reactions at the beginning to it can occur quicker.
There's more to react.
Yeah, that's correct. Click again. All right. The rate at the beginning is faster, and it slows down. We can calculate an average rate. If we were to, what is the rate of this reaction between 0 and 400 seconds? We could calculate an average, and the average would be a straight line like this meter stick. Nice straight line. But the reality is it's a curve, right? So we can find an average. At the beginning it'd be faster. At the end would be slower than the average. For the most part in this class, the rate that we're most concerned about is this right here, the initial rate, where it takes off. Okay? You can find an instantaneous rate anywhere on the line. Like if we want to know what is the rate right here at 100 seconds. If we had the graph, we can figure it out. The way we do that is we take the line tangent to that point. You know what tangent means?
So it's kind of like we're doing cases where it's like, at one point you can find the speed of the acceleration, and then overall on the average.
When I say the line tangent to this point, what does that mean? Tifa. When I say the line tangent to this point at 100 seconds, what does that mean, tangent? It's straight, yes, and it only intersects this curve at that one point. Okay, so this line only intersects that curve at that one point, so this is the line tangent. If you just extend it out a ways and then make a triangle, then you can look at this from here to here. This would be the change in concentration over the change in time, and you can calculate the instantaneous rate at that point, at that instant. And it doesn't matter how big you make the triangle. You understand what I'm saying? Take the line tangent, make a triangle out of that line, then find your change in concentration and your change in time. I'd have you do this on this slide, but it's not. I mean, we'd be guessing. I need the lines in there to make it a little more precise. Okay, and the farther we go along, the slower the rate is going to be. You can see the rate is going down. Click. Again. Okay, when you, I think you should all know this. When we're finding the delta, final minus initial, final minus initial, yes. So delta t would be your final time minus the initial time.
Yes.
Okay, click. Any questions about that before we go on? The average rate is not all that important in the big scheme of kinetics, nor is an instantaneous rate anywhere along there. The important thing is you know that it's going to go down over time, and we're going to be studying the instantaneous rate when the reaction first occurs. Click. Okay. That's good. Do you know what this means? When we use it in an equation, what does that mean? It's not an A. It's alpha. That means the rate is proportional to the concentration of VR. Okay.
Wait, what again? That's the
We've got a graph here. Is there one? Is there a, the equation is not on here, is it?
No.
Is there anything else on that slide?
No.
Okay, yes. Say that again. In this, proportional to. So in this reaction, the rate of the reaction is proportional to the concentration of the bromine. Okay? So we have rate on this axis, concentration of bromine here. Okay? So the concentration of the bromine is going up as the rate goes up as the concentration of the bromine goes up. The higher the concentration, the faster the reaction. Is that not what we saw with the oxygen at the beginning of class?
Yes.
We increase the concentration of oxygen, the rates sped up, right?
Does that mean we can increase the concentration of the, no, never mind. Oh, wait, does that mean, I'm asking. Does that mean we can increase the concentration of the iron and the reaction will be up?
No. If we were talking about iron in an aqueous solution, where there is a concentration of iron, yes. But right here, I have pure iron. I don't know how to get a higher concentration than pure iron.
So if
This is 100% iron. I can't make it more than 100% iron. Does that answer your question?
Yeah.
It's not a concentration. Like the oxygen in the atmosphere, there was more oxygen per volume inside the flask than there was out here. So we can increase the concentration of a gas. We can increase the concentration of an aqueous solution. We can't increase the concentration of a pure substance.
So if you're trying to burn like iron before, but mixed with other things.
Then the more pure the stuff, then you would be increasing the concentration. All right. So the rate is proportional to the concentration. Mathematically, we can insert a constant in there. So the rate is going to be equal to some constant times the concentration. We can solve for the rate constant by rearranging it. So to K, our rate constant is going to be equal to the rate divided by the concentration. And it's constant, so we get a straight line, not a curve. The rate is proportional to the change in concentration. Mathematically, we get a straight line from that. The slope is constant. Does that make sense? Okay, so in this instance, we have a rate constant of 3.5 times 10 to the negative 3 s to the minus 1. Do you remember what that to the minus 1 means? It's in the denominator, that's correct. So if you look at our units, when we're doing rate constants, I want you paying very close attention to the units because you can learn things about the reaction from the units. You'll see that in the coming days. So my units for the rate in this are molarity per second, right? So we've got that in the numerator. In the denominator, we have concentration, so that unit is this, right? Molarity cancels molarity, so we're left with seconds in the denominator. We indicate that by s to the minus 1. Okay? The units will not always be s to the minus 1, but we'll get to that.
Well, what does that tell us about the reaction?
It's first order.
What does that mean?
I'll get to it. Yes.
When you said that the rate was is C alpha Br2, or the concentration of Br2, that means it's proportional, meaning it could also be rate is equal to the concentration of Br2?
No. Only the rate is equal to some constant times the concentration. And we can insert a constant because these are proportional and we get a straight line from it. That constant never changes.
Got it.
Does that make sense? This is how the constant is useful to us, and we can derive it mathematically because the rate is proportional to the concentration. The more the concentration goes up, the more the rate goes up. They go up in the same proportion
The constant never changes for that element?
for that reaction. for that reaction,
That specific reaction.
unless the temperature changes.
Oh, yay.
Oh, that's not
Okay, but for the most part, the temperature won't change.
Temperature changes all the time.
We're in kids.
For our data, it won't. All right, factors that affect reaction rate. Again, this is the qualitative analysis. This is what you're going to be writing free response answers with. This is important. Just as important as crunching the numbers.
Is it qualitative or quantitative?
Quantitative means numbers. Qualitative means you know what's going on. So the reasons rates change. Temperature changes the rate because of collision theory. We understand kinetic theory, right? All molecules are in motion. Hold on there, clicky girl. The collision theory. When two chemicals react, their molecules have to collide with each other with sufficient energy for the reaction to take place. And if they're a big molecule, they have to have the right orientation. They have to hit the right part of each other.
At the right.
With enough energy to cause the reaction to occur. It takes energy to break bonds apart and then they release energy when they form new ones.
So the more complex the molecule,
The more complex the molecule, the more important the orientation is of how they collide.
so the less likely they'll collide together, so it'll happen slower
Yeah.
or slower.
That could slow down the reaction, yes.
You need to-
You all understand kinetic theory? When we measure temperature, what do we measure?
How
Speed.
fast?
The average kinetic energy of the molecules in the air.
What's that mean, average kinetic energy?
It
How
means
fast the molecules are
How
going.
fast the molecules are moving. So if we increase the temperature, the molecules are moving faster, they're more likely to slam into each other, speeds up the rate of the reaction, right?
Yeah.
Concentration of reactants, the next thing that affects the rate. More reactants means more collisions, if enough energy is present. Click. Catalysts, speed up reactions by lowering the activation energy. We'll study that more later in the year. And surface area of a solid. So, back to our iron. This is steel wool works great for this because it's little pieces and it has high surface area. If I were to just take a piece of iron, I probably couldn't get it to burn. Like a chunk of iron would be less effective because it would have less surface area. Any questions?
Oh, okay.
Like, pressure of gaseous reactants or products. Why would increasing the pressure on gases cause the rate to increase? Ryan Patrick Henry Dempsey.
Because if you increase the pressure, that would mean that the molecules of the gas would be forced into the reactant and it would just cause.
Forcing them to be closer together, they're more likely to run into each other.
Yep.
Perfect. No.
Oh, so that's why, what did you just say?
If you-
Putting pressure on gases, we're causing molecules to be closer together, they're more likely to collide with each other.
That's why
That
we
is correct.
heat them up, because they're more likely to
Yep. Let me get that if you question.
Yeah, and the temperature, as we increase the temperature, they're moving around faster. A little bit like Ryan at a dance. Early in the evening, there's probably more girls available for him to dance with, the more that are there that he can ask, the better the chance that he'll actually find someone to dance with him. As the night goes on, people start leaving, it's harder and harder for him to find someone to dance with.
That's a great example.
Dude, come on, man.
That's better.
But,
That really, oh man.
all right, the rate law.
It's a law.
It's the law. You must obey.
Is that a real thing?
The rate law expresses